Video is going to show you how to solve an example problem for a magnetic field that's produced by a current carrying wire. So we're talking about Ampere's law here. First off, let's talk a little bit about the current. In physics, it's all about the study of matter, energy, motion, and force. We know that energy flows, or stuff flows, basically from the higher potential to the lower potential. On a battery, the positive side is the higher potential, the negative side is the lower potential. And we're talking about current electricity or energy flowing. We're talking about electrical charges that carry energy to a device. And those charges will travel from the higher potential to the lower potential. So the current is used to represent the flow of energy in this case. Therefore, the current is represented by the movement of positive charges. So positive charges will be repelled from the positive terminal, and that's what's delivering the flow of energy. So we're defining current as a flow of positive charge, which means when we're solving this, we're going to be talking about the right-hand rule. So if you're looking at current as a flow of negative charge, this video may not help you. So the question is, what is the magnetic field 10 centimeters away from a wire carrying 4 amps of current? So I've got the wire here on the left, and I've got a little dot, and that dot means it's the tip of an arrow coming out of the wire, so the current's coming out of the screen right at you. And I've got this dotted square on the right, the orange dotted square that represents the location in space where I want to find the magnetic field. So in order to find the magnetic field, I need magnitude and direction. The magnitude is created thanks to Ampere. So the B field strength is equal to mu naught I divided by 2 pi r. So mu naught is a constant. It's 4 pi times 10⁻⁷ Tesla meters per amp, and that should be lower. We'll go with it. Times the current in the wire, which is 4 amps, and that's divided by the circumference, 2 pi times the distance to the point in space. And without going into a whole lot of detail, it's just a piece of the circumference that we're after, which is why we divide it by 2 pi r. When I solve all this, that gives me 8 times 10⁻⁶ Teslas, and it's upwards. And here's how I know it's upwards. Here's how I know the direction's upwards. It's not because it's a positive answer, it's because of the closed right-hand rule. So in the closed right-hand rule, the thumb is the direction of the current, or the direction of positive charge, either way. So it's coming out of the page at you. So there's my thumb, and then I close my hand kind of in a fist with my thumb sticking out. And my fingers show the rotation or the loop of the magnetic field. So there's the magnetic field looping around, and I can see my fingers are moving in a counterclockwise direction, so that's the direction of the magnetic field. In tangent to the circle, at that empty space, I can see the B field goes up. That's how I knew it was upwards. So it's 8 microteslas, and because of my closed right-hand rule, what I'm figuring out, that's the direction, and it's going upwards at that point in space.